In all of our work so far, we've been assuming a bell curve that is normally distributed, meaning 3 standard deviations in either direction will encapsulate 99.7% of the information. But we've been working on the assumption that our population standard deviation was known, so we used z. But that's kind of unrealistic. So today we start answering the question, is the population standard deviation known? No. So we're going to use a new chart called the t-distribution, or students t. Each of those values represents a number of standard deviations from the mean, either to the right, giving you positive t table numbers, or to the left, giving you negative t table numbers, or what could be considered two tails, to the left and to the right, graphically shown on a standard normal bell curve. And these are the steps for how to use the t-table as a graphic or just as a t-table number. First of all, the numbers at the top are known as alpha. They're the percent we are willing to be wrong. Alpha is kind of a fish-looking thing, but it's the Greek symbol for the percentage that is in the tail. Step 2, we're going to use what's called degree of freedom. Degree of freedom is simply defined as whatever your sample size is, n, take away 1. And then you take your alpha number and your degree of freedom number and smush them together, and that will give you what's called t. For the sake of clarity, you saw in the chart, but I want to emphasize that t-table numbers are always given with 3 decimals. So let's try a few. If we're looking for the right-tailed value, would be on the right side of the bell curve. We're looking for the number of standard deviations when sigma is unknown that cuts off 5% in the tail, known as alpha, when there are 13 in the sample. This means degree of freedom of n minus 1 equals 13 minus 1, which is 12. So we go to our table and we find 12 degrees of freedom, and we trace that in together with 5 from 1 tail, because we're only here on the right-hand side, and we find a value of 1.782. Because it's to the right, we would use that value as is. The second example takes another one-tailed value, but this time we're going to be on the left side of the bell curve. Notice none of these numbers are negative, so any answer that we get, we'll have to put in the negative, because these numbers on a number line are less than 0, along the lines of 0, -1, -2, so on and so forth. So following our process, if n is 23, then the degree of freedom is always n minus 1, so 23 minus 1 gives us a degree of freedom of 22. So look in the degree of freedom column and look at 22. That's the line we're going to read. Last but not least, in this case, look to where you're going to cut off 1% in the tail. So alpha is 0.01 in the left-hand side, so we're reading this column right here, 0.01, trace it downward to find a value from the chart of 2.508. Remember, because it said to the left, the numbers are negative. Similarly, this question says two-tailed, so read the two-tail line. It's going to tell us that alpha is recognizing 1%. So find a two-tailed alpha 1%. We're reading this column. Last but not least, degree of freedom is 25. Since it's given as degree of freedom, we don't have to do any subtraction. Degree of freedom is what the chart runs on. So I look at 25 degrees of freedom, and if you're thinking to yourself, does that mean that there were 26 in the sample? You'd be right. Read the line for 25 degrees of freedom, and then figure out where those two pieces of information are going to intersect. 1% at 25 degrees of freedom gives you a value of 2.787. But one more time, since there are two tails, the positive version and the negative version, you have to note it that way. So here's an expanded version of the same chart. Just for fun, let's make up a problem and say that we are looking at n equals 42. And we want alpha to be one-tailed to the right at 5%. According to what we know so far, that would mean we go to one tail, we're reading the 5% line. But when I go to look for 42, it's not there. When this happens, you go to the closest lower. In this case, n equals 42 does not exist, so I go to the closest lower, which would be 40. Reading that line, I can see that my answer here would be t equals 1.684. Or for instance, if we want alpha to be to the right at 5% again, but now we have n equals 77. Even though mathematically you want to round up, we must go to the closest lower df and read 70 on this chart. Different charts will give you different values, ever so slightly off by about 1/1000th, but sometimes that makes a difference. The value here, based on this chart, would be t equals 1.667, and because it's to the right, it stays positive. So if n is 125, which again doesn't exist, go to the closest lower df, which would be 100. We're looking at alpha is to the left, so we would read one tail, and it's 10%. Where those two crash would give you an answer of 1.290, but because it says to the left, it would be here. To tie things together, it would look 3 sigma limits on each side. We would have negative 1.290 right here, cutting off 10% of the curve. So for our last example, let's look at what happens if n is huge. Let's assume n is given as 1,888. The degree of freedom then would be 1,887. Not on the chart, so we choose the one that's closest. There is nothing closest. So what will really wind up happening is we go to the infinity line. Turns out the infinity line mimics the z-score table. So if I was told to do a two-tailed test with alpha equal 0.05, knowing that I had a huge n, in other words, something bigger than 1001, I would read my two-tail line, find 5%, crash those two together to get a value of 1.960 that is both positive and negative because of the nature of it being two tails. If you have a huge number, it mimics the z-score, as in pretending that sigma is known.